All right, folks. Welcome back to Moonshine Radio here. I'm your presenter, Dr. Moonshine. And today, folks, we're going to talk about some very common or basic architectures today for radio receivers. And specifically, they're called direct RF sampling. That's one architecture. Another architecture is called IF sampling, or intermediate frequency sampling. And lastly, the last type of architecture is called zero IF receivers. And today we'll give a quick talk of all three and explain them as clear as possible. Okay, well, quite simply, direct RF sampling is simply that. We sample the RF signal directly. In today's world, this is generally limited to only HF signals. So if we basically, it's a function of the A to D. So the A to D we show here is running at a clock of 125 megahertz. So that A to D by itself is able to sample an RF signal anywhere from 0 hertz all the way up to 62 megahertz, as shown below, half the clock. So if you're interested in, let's say, picking up 4 megahertz signals, this would be an approach. You'd have a 4 megahertz antenna, maybe a 4 megahertz amplifier, and probably want to have some kind of 4 megahertz filter such that you're only picking the bands that you're interested in, and then you sample it. And then after it's sampled, it goes into what's called a digital down converter to convert that 4 megahertz signal to baseband in the digital domain. And if you're not sure what a digital down converter is, go see my video on that where I talk about just the digital down converter. But anyway, this here is a example of what is called direct RF sampling. So in reality, if you're interested in a range of frequencies, you would probably, or a good receiver, would have a range of bandpass filters that it would select based upon what you want to receive. So this is probably the best receiver you can get. As you can see, there's no mixers here, so we don't have to worry about mixer products or any kind of thing like that. It's basically get the signal close to the A to D as possible. And as that clock rate keeps going up and up and up with technology, this direct sampling approach will, be at VHF and higher. So it's just as the A to Ds get better and better, we can get the A to D pretty much right on the antenna. And that is the holy grail of radio receivers. Now, that A to D, the guy on the triangle here, it's a pretty nice chip. But I have a signal maybe up at 2 gigahertz. Can I still use that A to D? Of course the answer is yes. But now you have to do what's called an IF sampling receiver. And that's what's shown here. So let's just say we're interested in picking up signals at 2 gigahertz. So we'll 2 gigahertz antenna, some amplifiers, probably run it through a 2 gigahertz bandpass filter. Then that will hit a mixer, or could hit several mixers, but for our case, let's just say it's one mixer. And we're going to down convert that 2 gigahertz signal down to 40 megahertz. And then 40 megahertz, we will then digitize that and then have that go into our digital down converter. We will set our numerically controlled oscillator in the digital down converter to be 40 megahertz, and that will convert that signal down to baseband IQ. So this is an approach of what is called IF sampling. Basically, we are digitizing the IF frequency as opposed to the RF frequency. And this is what you have to do when you're interested in very high RF signals that simply the A to D cannot sample directly. Quite simple. So we have to use mixers, local oscillators to shift that high frequency signal down to an IF signal that can then be digitized. And this is very common still today for high frequency signals. So this is what is called IF sampling. And The A to D still has the same range. It can only see signals from 0 to half the clock. So generally they make the IF 1/4 the clock. You don't have to, but that's probably a good method. I guess if you were interested in smaller bandwidths, you could maybe make it 1/8 the clock, just so you get some more samples. But this is what is called IF sampling. So far, pretty straightforward. And lastly, I will show you what is called zero IF sampling, or some people might call it analog IQ. I personally think this is the worst idea because you have to deal with all the mixer products, DC leakage, the quadrature imbalance. So if you see an architecture that looks like this, I would run away, because what this means is that now someone, or the vendor or whoever made this thing, hopefully, is going to have to implement some kind of IQ balance cal to correct all these analog mixers, phase splitters, and everything else. When you do all this in DSP, it's much more cleaner and doesn't have any analog artifacts. So this is unfortunately still used. I think the trend is that this is getting replaced with either direct sampling or IF sampling, such that this IQ cal problem can be eliminated. But it's still around. This is what's in your hack RFs, and your USRP products, unfortunately, still use this architecture. So if you're in just digital communications, you can probably live with some of these artifacts not being so ideal. But once you get to more arbitrary type waveforms, this architecture is very bad, and I would steer away from it. So how would this work? So if we want to, let's say, pick up a signal at 2 gigahertz, we would simply just set that PLL VCO to exactly 2 gig, such that 2 gig minus 2 gig is 0, and the signal has been shifted to baseband in analog domain, and then we would sample the I and Q, and then that switch digital. The problem is the two mixers are never going to be exactly equal. The 90-degree split's never going to be exactly 90, and you have to calibrate all that. Otherwise, you're not going to have really quadrature signals too well. So I would steer away from going down this route for any new designs, but it's still around, and I just wanted to show what do people call zero IF sampling, or some folks might call this what's called analog IQ. Well, very simple talk. Hopefully that explained everything for everybody. If not, you can certainly Google those three terms and get a much more detailed analysis. Bye for now.